So let's go ahead and get started. So if you hadn't turned in the tutorials yet, you can turn them in at the end of class, but we'll go ahead and get started here. So last time you'll remember we were talking about electric potentials, electric fields, forces, electric potential energy, and I drew this chart that related all of these things together. So the first thing that I want to do today is go through two of these charts that you guys are going to fill in yourselves based on some initial conditions here. So for this first one, what I did was I told you that you have some constant electric field in the positive x direction, and I have this picture in the bottom left corner so that you can visualize that. And what I want you to do is I want you to go through and fill in all of the rest of the blanks here. And also there are some additional questions to go along with that. So if you go to Learning Catalytics, the first question that we have here is actually just a series of questions related to this chart. And so the whole reason why we're going through this with these two is, you know, it's all fine and good to have equations and then say, okay, well, if I need to solve a problem, I know I need an electric potential, I pick out an electric potential equation. But real deep understanding when it comes to these types of questions is understanding the relationship between these four quantities and how you can go from one to another. And ultimately, when it came to our electric field and our electric potential, this portion right here was how we were talking about our equipotential lines and what it meant when we had a lot of them close together, or if they were sparse, what that had to do with the magnitude of the electric field. So go ahead and start up your Learning Catalytics and start going through these questions, and then we'll be walking around guiding you guys through this as you go. Okay, so let's go ahead and talk about this one. So let's just go question by question. Let me first write down my electric field vector here. So I gave you this picture where this electric field is pointing in the positive x direction, and it's going to be uniform and constant, just going in the positive x direction. And this electric field was equal to just the magnitude of E, so it's just some quantity E, times x hat. Okay. So how could we go from electric field to force if I say I wanted to put a test charge in here, if I want to put a charge in here? How could I go from this to this? What was the equation that allowed us to do that? You guys know it. I saw a lot of you had it. Yeah.
Multiply the charge of the particle times the field.
Mm-hmm. Right. So you say that the force, F vector, it's a vector sign. Let me move that down so we can actually see that it's a vector sign. F vector is equal to Q times E vector, right? Now this is a general equation, and the way that you're going to go from electric field to force will always have this equation, right? Now we want to get into the specifics of this arrangement that I gave you here to find what the force is on here. And so we can use this equation that I have written here and this electric field. I can plug this in here, and what I see then is that the force is going to be equal to Q times the magnitude of E times x hat, right? Now let's pause a second and see if this makes sense with our picture. I can put this charge anywhere in here, right? I can put it here, I can put it here, I can put it down here. And the force that it feels is always going to be going in this direction, and it's always going to be a constant, right? Times its charge, if it's positive, right? So if it's a positive charge, it's going to go this way. If it's a negative charge, it's going to go this way. Okay. So then the next thing that I wanted you to do is I wanted you to go from the force to the potential energy. So conceptually this is a little bit tricky to think about, but the way that we can think about it is with a parallel parallel, and that's to say that if we had a mass here, so call this some mass of m, and we moved it up or down in the presence of the gravitational potential, we could say that it changes gravitational potential energy. And it's the same thing here. If I move this charge around, I can change what its potential energy is. Okay, so what was the equation that we had to go from one to the other here? Yeah.
F equals negative delta U over delta X.
Yep, perfect. So F is equal to negative delta U over delta X. Now, to get this delta U, we can rearrange this. So we multiply both sides by delta X, and then we plug in F. And so what we find then is that delta U is going to be equal to negative Q times E times delta X. Okay? Now, the one that I asked after that was how do we go from electric field to electric potential? Now this equation, because we're going from our vector equations to our scalar equations, this equation and this equation look almost exactly the same, right? So what was this equation? Somebody else, somebody new. How about somebody over here? What do you guys think? You had it, I saw him walking around. Looks a lot like this. You guys are really quiet today. What's the deal? It's Thursday? How about somebody else? Somebody over here, yeah.
It'd be the Q equals negative delta V. Not that.
Q is equal to negative, hold on. Q is equal, say that again?
Negative delta V over delta X.
Yes, E is equal to negative delta V over delta X. Right. I might have just misheard what you said. Okay, so this is the way that we're going to go from this one to this one. Okay, so we can do the exact same thing that we did here, right? That we did here. We plug in E into this equation and then solve for delta V. And when we do that, we see that delta V is going to be equal to negative magnitude of E times delta X, okay? Now, there's another relationship that we can connect these bottom two with, right? So we can connect this one to this one. How is delta U related to delta V?
Delta U would be delta V over charge.
Other way around, delta V.
Would be delta U over charge.
Yeah, this is Q times delta V, right? Yeah, good. Okay, so that completes the table, but I also had a couple of other questions about the way that these two are related to each other via the equipotential lines. So we also wanted to draw some equipotential lines here. So what are those going to look like? How do equipotential lines always look relative to electric field lines?
Normal.
Yeah, they're normal or they're perpendicular, right? So what does that say about them here? They're just going to be vertical lines, right? How are they spaced? Is it like that? Equally spaced, right? So let's get rid of these ones that are not so equally spaced. So these are going to be equally spaced, okay? So these are going to look like this, okay? So then, what I wanted you to do is I wanted you to think which one of these sides is going to be at a higher electric potential. We know electric field lines point from what to what?
Positive to negative.
Positive to negative, right? So higher, lower, lower, higher, lower, higher. Which one? This one should be higher, right? This is low. Okay, so let's put these two things together and think about how we could plot delta V, right? So we could equivalently write this: V as a function of X is equal to minus the magnitude of V times X, right? What does this look like if I'm going to plot V as a function of X here? It's just going to be a line that goes down like this, right? So this is going to go down like this, right? So does this make sense with what we have here? Well, we have a high potential here, a low potential here. These are evenly spaced. So this line, it shouldn't be curved, right? It should just have a constant slope like this. Now, if I ask you what the slope of this line is, what is the slope of this line? It's constant, yeah? It's a very specific constant for what I have written here too. Look at this equation that I erased. Look at E is equal to negative delta V over delta X. This is, I'll draw it even more explicitly. So between 2 points, this could be delta X, this would be delta V, right? Because on the y-axis I have delta V, on the x-axis I have delta X. So this slope is, it's the negative electric field, right? Negative electric field, okay? And that's exactly what this equation is telling us here, okay? Does it make sense? Yeah. So let's do another one. So this one, we actually already, some of you already wanted to start doing this. Now, this is for the spherically symmetric case. So now instead of giving you a constant electric field, I'm telling you that for some negative point charge, I have some electric potential. That is, V is equal to K times negative Q divided by R. And I want you to go through exactly the same process and fill in the rest of this table. And also make sure as you're going through this process, you go through this argument that I just went through here with the equipotential lines and looking at what the slope of V as a function of R in this case is. Okay? So take some time to do that. Talk about this one and then we'll move on to some more questions. So for this one, we kind of realized that we couldn't quite just go from the electric potential to the electric field the same way that we did before. And that's because when I plot this electric potential, unlike before, so if this is V. This is V as a function of R, or sorry, this is R. This is R, and this is V as a function of R. Now it has this behavior, right? Unlike the one before, this isn't just a flat line, right? It's not, it doesn't have like a nice slope that we can calculate using our rise over run method. And so if you wanted to find what the slope of this is, you'd actually have to use calculus to do that. But we do know that the electric field is related to the electric potential via that slope at a point here. Okay? So because we knew that this was a spherically symmetric system, and we had a negative charge here, then we could just write down what the electric field was by saying that this is just going to be E vector is equal to minus K Q over R squared times R hat. Okay. Now, to go from the electric field to the force, if I say, okay, I'm going to bring some positive charge close to this, what's the direction of the force acting on this? Then I'm just going to take this equation and plug it in here, and so F is going to be equal to minus K, and we'll just say that we have some Q1 and Q2 here now, divided by R squared times R hat. And now to go across from our electric potential to our potential energy, we do the same thing that we did to go from here to here, and so we can say then that this is U is going to be equal to minus K Q1 Q2 over R. Okay. Now let's answer the questions that were related to these two in terms of what these equipotential lines look like. So I kind of asked this question these questions in the reverse order that we might have seen them before, right? So before we just say, okay, I have a negative charge, I'm gonna say that it has field lines that point in, right? Well, instead of asking that first, I asked, what do the equipotential lines look like here? So what do the equipotential lines for this negative charge look like? Those are the electric field lines, right? So yeah, they're just going to be concentric circles that go around here. So we know that these are circles that go around here. Well, these circles correspond to these points on this plot, right? The values of these circles are the values of this plot. So what can I say about this one relative to this one? Is it more or less? We're looking at this plot, right? Is this one more or less than this one?
Less.
It's going to be less, right? This is lower than this, right? So this, I could say is, we can say this is like a minus V and a plus V. How do we know, what direction do electric field lines point when we talk about equipotential lines? Do they point from positive to negative or negative to positive? Positive to negative. So if I was to draw the electric field lines knowing that this is a higher potential than this, then I know that it points in like that, right? And that's exactly what we had said before when we used the reverse definition. We said, okay, well, we had some electric field that's just defined like this, then it has electric field lines that point in because this is a negative and then this is an OR hat, okay? So we can see how these two can talk to each other on that level. Okay. Any questions about this one? Okay. All right, so let's go do some actual calculations now that we're kind of past the conceptual part. So we're going to go back to this one that we left off on last time, and keep in, maybe not so much for this one, but as we're doing some of the other ones, keep in mind these tables that we drew here and how these things are related, and these plots here, they're all helpful for understanding the problem. I'm going to draw some things here. I'm going to let you guys talk me through that, and then I'm going to give you a little bit more time to answer this, because I think some of you might be a little bit confused here. So this kind of goes back to those plots that I had drawn over here before, right, for the last two problems, because it helps you visualize problems like this. So to answer which one of these requires the most work, or you know, if they're the same, what we want to do is we want to plot what the potential is versus the distance. Okay, and do that for all three of these. Okay, so for the first one, where do we start? In potential, what's the value of the potential where we're starting?
150.
It's 150, right? So we say 150 is up here. So we say this is 150. And then we go to 100. So it's less. So this goes down like this. So that's 100. Then for the next one, we start at 25. And then we go down to minus 25. I should do a better job of drawing this to scale, because that's the whole point of what I'm doing here. Okay, so then for case 3, we're going from minus 60 to 10, right? And minus 10, right? So that's going from down here to up here, right? So if we looked at what the magnitude of the change in V is, delta V, or the magnitude of delta V, is going to be 50 for all of these, right? But there is a difference here, right? And so that's really the key to answering this question, is understanding what the difference is between these, okay? So in this analogy, we can talk about this in terms of like climbing a hill, right? So how difficult is it to climb this hill? Geez, I need to learn how to draw. How difficult is it to climb this hill versus this one? It's the same, right? Because I'm just going down. It's the same distance that I'm going down. How about this one? This is harder, right? Because I have to go uphill, right? So what is the difference between this and this?
Voltage.
The voltage, right? So the initial voltage. What could that correspond to with our hill analogy?
Height.
Right, so the initial elevation of this. So if and of course it probably does matter because atmosphere changes density, so it's harder to climb, you know, at the top of a 14,000 foot mountain. But imagine that's not true. We can make the mountain as high as we want, and as long as the distance that we go down in y is the same, it doesn't really matter how high it is, okay? So the answer here should be C. So we're given that there's some decrease in potential for some positive charge, and we want to know what the change in kinetic energy is. So in order to do this, what we need to do first is to say that delta U is going to be equal to Q times delta V, and that delta U is equal to minus delta K. Okay, so we can take this and plug this in here, so then we'll get negative delta K is going to be equal to Q times delta V, and then we can just plug in what we need. So Q is going to be 2 times 1.6 times 10 to the negative 19. Delta V is going to be what? Now this is where we have to be careful here. It's negative 500. Why is it negative? Because it's a drop. So we can get negative 500 times 2, which is going to make this 1,000. So we have negative 1 times 10 to the 3 times 1.6 times 10 to the negative 19. So this is going to be equal to 1.6 times 10 to the minus 16. And that is our negative delta K. And then this becomes positive. So the answer should be C. So you have to be, with these kinds of questions, you need to be careful carrying through all of your negative signs, right? Okay, so we got another one like this. Now this one again, be very careful with the way that you're carrying around negative signs here. Let's talk about this one. I feel like I say that every time. It's like I start class the same way every time. Okay, let's go ahead and get started, and then, okay, let's talk about this one. I need to think of new things to say. All right, yeah, I think I say all right sometimes too. Okay, all right, for serial now, okay. So we want to find what the electric potential is at this side, right? And so what I did to represent this this question, we're told that we have two parallel plates of a capacitor that are separated by 2 centimeters. And that one side has an electric potential of 45 or negative 45 volts. We're given what the electric field is, and we want to find what the electric potential is on the other side. So we know that this is 45 times 10 to the 3, correct? Yep. Newtons per coulomb. And so we want to find what this V1 is. So that's not really the way that the problem was set up, but it helps to draw these things so it's very clear, okay, I have an electric field that points from here to here. I have two electric potentials here. I have a separation of 2 centimeters. So this makes it a lot easier to set up and solve, and then you'll know you're getting the right answer. So what we want to say is that E is equal to minus delta V over delta X, right? And then we can move this around, so we have negative delta V is equal to, let's actually bring the negative sign to the other side. So this is delta V is equal to negative E times delta V, or delta X, Thursday. So then what we want to do is we can expand this delta V, so this becomes V2 minus V1 is equal to negative E times delta X. And we want to solve for V1, right? So we can move the V1 to one side, we can move the E times delta X to the other side. And so then we have V1 is equal to V2 plus E times delta X. And this is going to be equal to 45 volts when I plug everything in. Okay. Now we can check to see if this answer makes sense. I mean, it might not, it could be possible we plugged in the wrong numbers or something, but at least the physics should make sense here. If I have, this is at 45, right? So if I say that V1 is 45 and V2 is minus 45, does it make sense that the electric field goes in that direction? Yeah, because it's going to go from a higher potential to a lower potential. Okay. All right, move on to the next one. I did again. Need new catchphrases, all right. So the first one, we want to find what the electric field is midway between the charges. So for point charges, we had this equation, E is equal to K Q over R squared times R hat, right? And we can look at this system of charges and notice something kind of interesting. If we're finding what the electric field is at the midpoint, the distance from this charge to the midpoint and the distance from this charge to the midpoint is the same. And these also have the same magnitude of charge. So to find what the electric field is, I know that the positive charge points this way, the negative charge points the same way. And so I can say that the electric field E in X is going to be 2 times 9 times 10 to the 9 Newton meters squared per Coulomb squared times the charge, which was 2 nanocoulombs, so 2 times 10 to the minus 9 coulombs, divided by the distance to that point, which is going to be 0.075 squared, and this is going to be equal to 6,400 newtons per coulomb. Okay. So now if we want to find what the electric potential is at this point, we have to use the equation that V is equal to KQ over R. And we can look at this equation and say, okay, well, if I want to find the total, this should be V total is equal to KQ over R plus K minus Q over R, right? The distance is the same, the charge is the same except for a negative sign. And so what that means is that these are going to cancel, and so this is equal to 0. Now to find the force, we know what the electric field is already. So to find the force on a charge that we put at the center, we just take this electric field and we multiply it by the charge. And so F is going to be equal to QE. And so this is going to be equal to 1.9 times 10 to the minus 6 newtons. Okay? Any questions about this one? Okay, so we'll hop into, do one of these circuits and I'll let you guys go a couple of minutes early. Okay, so the next thing that we're going to be talking about next week is going to be circuits. And so the real thing that connects what we've been talking about so far and circuits is the electric potential. So when we talk about circuits, differences in electric potential are what we call a voltage. Okay, so go ahead and think about this question that I have here and talk to each other and try to figure it out. All right, so giving you guys a little bit of time to talk about this. Talk to me now. What direction are the electrons going to flow here? Negative to positive, right? Because again, we can draw some hills to understand this, right? So we can say we have some negative here, right? So this could be like a minus V1, and this could be a plus V2, right? We put an electron on this hill. Electrons are, they're industrious and they're proud particles, and they always want to rise to the occasion, right? So they always go uphill, right? So it's going to go from the negative to the positive, okay? So that's going to be it for us today. You guys have a good weekend, and we'll see you on Tuesday.